This is section 16.2, which is line integrals, and we finished example 2 in class, where we did our line integral along C, which we broke up into 3 parts here. And so the one we're going to do now is the same line integral, except C is a little different. It's going to go from this endpoint here at -2, -1, directly to 1, 2. So this is example 3, and here is the line segment. Same integral like I said, and then C is this line segment that goes from -2, -1 to 1, 2. So here's where we're going to encounter this vector equation of a line, and we're going to use the line segment form of that because that's what we have is a line segment. And so at the beginning of class I had talked about how to do the parametric equations for that and where it comes from. So we'll just take that. This is the 3D situation, but it's easy to reduce it by taking out the z. So another thing we learned is that when we do the line integral according to ds, or the arc length, then we don't have to worry about the direction. So if you chose to let your r naught be equal to -2, -1 versus 1, 2, it wouldn't make a difference in your answer. I'm just going to go with letting our r naught or x naught and y naught pair be -2, -1. And so that means that our x sub 1, y sub 1 is 1, 2. Plugging into the parametric equations for x, after I simplify, I get 3t minus 2. And then for y, I get 3t minus 1. The way that these equations, the parametric equations, are set up, this is going to be when t equals 0 to t equals 1. And so that's already determined, and we can go ahead and plug all these things into the line integral. So for x, we're plugging in our little x equation in terms of t, which is 3t minus 2. And then for our ds, we're going to be given this where we have to do this conversion here with this little byproduct thing that we find dx over dt, or that derivative of x with respect to t, the derivative of y with respect to t, do that little calculation there and you get square root of 18. So our 0 and 1 in this integral come from, again, that this line segment, we're setting this up so that our parametric equations will have t equals 0 to t equals 1. That was by design. So we plug that in there, and then this one you could expand it out by taking this binomial times itself 2 more times, or notice that with a u sub that might be a little bit faster. So let u equal 3t minus 2. Take that derivative and you get 3, and then we can modify this by having a du over 3 with our u sub. Not such a bad integral. And we go through the motions here to get our result. So one little point to make before moving on is that we got an answer of -15 times the square root of 2. And this was the same integral as the previous example, example 2, except it was along a different path. And for this one we got about -5.732. So just making a point here, a little hard to tell with this not being actually written approximately, but they are different results. They're not very close. And when you take a different path, then we get a different answer, which is probably not surprising, but just a little point to make there. So moving on to 3D, we have a very similar equation here for the line integrals, just adding that z component. And this is still a 1D integral, so to make that point that what's going on here is we do have a function that's defined in 3D space by this location, but the integral we're taking is still a line integral in 1D. So one example would be along a helix, and this is an equation, parametric equations that we've seen in the past. And this r can be characterized by cosine t, sine t, and 3t, where t goes between 0 and 4 pi. In this one, we're just going to set it up in terms of t. We don't actually have to evaluate. I started evaluating it, and then I realized that we needed to do use a trig identity, and we also needed to do it by parts. So I set this up as to be a one that would be good just to set up for that reason. So anyway, we're given the parametric equations here, so that's kind of nice. We have our x equals to cosine t, or y equals to sine t, and our z equals to 3t. So that's given when it's given in this vector form. So for this equation here, we have things that we need to plug in. Here we're taking this line integral of x, y, z. And so all those things will be plugged in here from our parametric equations that were given in this vector form. And then we need to find all those little derivatives. And so doing that, as some side work, we get negative sine t, cosine t, and 3. So plugging those in, and then we have a square root of all those derivatives being added with their squares, and we kind of have a mess. So put the limits of integration in there, and then for this problem, that's actually all we need to do.